Hi, welcome to this new video of this lecture series. This is the lecture number 8. Before going deep into this lecture, I think in the last 6-7 videos, I tried to discuss about the timing analysis, basic definition. Then we went for the static timing analysis and dynamic timing analysis difference. And we know that most of the time we check for the static time analysis. So the static time analysis, there the timing constant, most important timing constant, we know that that setup and hold time. But this video maybe it's important for some of you, maybe it's not, but I would suggest that listen for some of the minutes, because it will give the uh, very good flavor of arrival time computation and required time computation and the concept of slack. This is also a part of very basic definition, but I would say that this is not a here I didn't discuss about the arrival time and required time, which you may be seen or you may know in setup and hold time equation by equation. Here the arrival time and required time computation we mainly talked about. In the which part I need to show you that several times we maybe discussed about this type of sequential circuit, which may be a part of very big sequential circuit, but that we generally computed arrival time in this pathway. Now I want to talk about mostly in this part, that combinational circuit part. Let's go for the arrival time computation. Okay, there can be a three type of scenario can happen. One of the very basic scenario is that when there is a only one incoming edge. uh, what is arrival time type of things, why I am talking about that. Let suppose there is a this type of condition about your simple combinational circuit. Suppose I try to draw like one. I try to give one example so that maybe you will understand that there may be this type of things. Okay, I just taken this example, but how to understand why the arrival time and required time need for to calculate for this one. Because as you know that whatever the circuit may be, you have to represent it into the timing graph. Okay, so when you do for the timing graph, there can be several type of conditions. You always do the forward traversing, not a backward one. Backward one happen in the required time. I'll come into that. But let's take some of the case. As I written here, that the time at which a signal settles at a given vertex, I need to know about that time. How I know that time? So that's why there can be a three type of scenario. Let's try to draw that scenario. One of the scenario can happen like that. One edges and there is another edges. There is a two vertex. Suppose this is a vertex I and this is a vertex J, and in between obviously there is a net delay. So I define this net delay as a dij, and because we try to take it as a input node or input vertex, so I can write it as a ai. Suppose this arrival time of this I node, maybe if this is a source vertex, then this arrival time obviously should give by the constraint, or maybe some way you know. Okay, then you try to compute the arrival time of that aj vertex. So you can simply write the formula that aj should be ai plus dij. The arrival time of this node aj should be like that in simple way. There can be a case too when there are multiple incoming edges. The multiple incoming edges, it's a simple type, like how to draw that. Let's check how to draw that. This is one edges, this is one edge, this is one another edge, and there is another edge. So obviously three type of edges will be there. So let try to um, I1, I2 and I3, three edges, and this you can take this is a j edge. So obviously if I assume this is the input or source edge at the particular point in a particular logic circuit, and I basically what I done that, from timing graph that this is the one of the logic gate or one of the basic gate. I just implemented in a source, and it can be different in the path based analysis, graph based analysis may be different in a different way, but just for now just take it as a simple one. So suppose there is a arrival time mentioned here is a 10, suppose here arrival time is mentioned 20 and it is a 40, and maybe that every edges have a different net delay, or maybe have a same net delay also, we don't know. Just for now assume that this net delay is 50 picosecond, this may be a like 40, this may be a 80. So you will, what you will do, if you want that maximum or minimum, you will go for that. You don't know, basically, like suppose for setup analysis you will go for the maximum arrival time, and for the whole analysis maybe you go for a minimum arrival time. And so this type of scenario can happen. Then can come to another scenario that this scenario is same as like this one, but there is a catch. Like I said here that a boundation on the arrival time at a given vertex. Okay, how we can represent that? Let's copy it and I will give you how to represent that. So this is on the same one. Let's keep that 50, 40, 80 as the same, but here what I said, here I said that bound on the arrival time. So suppose till now we know the only one arrival time for this every node. If I know that maximum and minimum arrival time for the every node, suppose take it example as a 100 comma 10, suppose this is was a 150 comma 20, so this is a 120 comma 40. So now for this j node, how to take the bounded arrival time, and you want to write that now. So follow that same formula. You can simply say that for the simple case I would suggest that take the every net delay as a 20 picosecond. It will be easy for you to understand. So the boundation will be for the maximum one 150 plus 20, so there can be how much, 170. The minimum one was what, 10, 20 and 40 is a 10, so 170 comma 30. So in this way I also can store the bounded type of arrival time. For you I tried to concise one note for arrival time, whatever the arrival times note, that arrival time is computed and stored at each vertex in a timing graph. I multiple time I told that. And arrival time at input ports specified by the constant, or you can assume to be 0 also. And obviously this is a forward traversal of the timing graph. A complication can also happen, that because that these all are the input, these all are the input vertex of maybe one of the particular position or instance. You don't know, we all are assuming that. So whatever the input signal may be coming here, that input signal you don't know na, how much slew it maybe. This signal can be this one, this is steep. So you don't know about computation can be complicated more if we talk about the maximum and minimum rise and fall time. So that complication can vary different level also, but I don't want to talk about here. It's just for your note, you will take it as a concept. Now coming to the required time computation. Required time computation is we generally do that backward traversal of the timing graph, and The backward traversal of the timing graph, when we do that, the required time computation is discussed about 2 times when I was writing the equation of the hold time and setup time. So for required time computation, it is very simple. Why I said it as a simple, that try to remember when I was talking about that setup and hold time equation. If you remember that for setup one, I talked about that the required time should be greater than that arrival time. Okay, and this is max analysis. We all know that this is max analysis, and hold time, that required arrival time or required time should be less than of that arrival time. Okay, that suppose this is the j1 and j2 and j3, and this is the I node. I represented in the timing graph, and obviously I already said that this is a backward traversal of the timing graph. If there already defined that the timing boundation at the particular output source, then you have to calculate the timing boundation at this I point. How to define that? There is a formula that so if you try to calculate the timing boundation at this I point for the required time computation, then you go for this formula, that is Ri hold, it should be maximum of Rj hold minus Dij. What is Dij? You know that this is a Dij, and if I take it as 10, 10 and 10 for everything, then you can calculate simply, and Ri setup, then this should be like minimum of Rj setup minus Dij. So by that formula, if you try to calculate, then you will land up at, take for the whole time, so take 15 as a maximum one, that Ri hold, take it as a maximum 15 and minus 10, so it should be like 5 comma minimum as a 100, minimum for this one, minimum 100 minus 10, so 90. So there it is a simple one, 5 comma 90. So till now I think you understand that arrival time computation and required time computation. Now based on that, oh sorry, before that there is a simple concept I note it as, if you try to read, this is simple. This one I already discussed. Obviously that required time for any port, or maybe the output port, or at the timing endpoint, is specified by the is this is constant, obviously constant, or it should given the simple word, and obviously that it's a backward traversal of the timing graph, constant primarily determined by the clock period. Okay, for the setup time, I think, by if you remember the formula, then obviously required time mostly dependent on the clock period. Now coming to the slack. Slack is important because by analyze the slack, or if you know the slack formula very easily, then you can give a view on setup and hold violation, if slack is negative, positive, or zero on that. That slack is just sometimes the required time minus data arrival time. Most of them, I think, if you found there is a mod in between, this is also same thing, because sometimes the arrival time is higher than required time and required time is higher than arrival time, same. So three type of case can be happen, and slack is basically that how much delay, if you compute the slack, you would land up as a view analysis, that that the particular slack number, it can say that how much delay margin you have for that particular logic portion. Okay, so slack can be a zero when obviously if the required time and arrival time is same, and the the design we have minimum clock period, obviously maximum clock frequency. If slack zero, if slack has a positive, obviously slack is a positive, it means that the data arrival time is lesser than the data required time. This simple truth we need in setup time, because if you remember the setup violation formula, then obviously it says the same thing. So if there is a slack is positive, obviously there would be no setup violation, but obviously slack is negative, then there is a setup violation. So this is one of the example I want to give so that you can understand the arrival time and required time and slack is very well. If you see very consciously, then you can observe, suppose this is one of the part of the combinational data path, which are in the between of two flops. This path also have delay. Okay, I have to draw the timing graph, and then I'll specify some of the timing constraint. I will assume that some of the timing constraint in the input when we try to cover the arrival time, and same when we try to cover the required time. That time also I will assume some time at the output node. So let's try to visualize in the timing graph. How to draw it, I think several times we also discussed about, but let's just I have to represent it in the vertices and edge. So how to represent? Simply there is a one I1 edge, there is a I2 edge, I1 vertices, I2 vertices, and I3 vertices. Write it as a I1, I2, and I3. These are C2 of A, and then there is another vertices which is of C1 of A, and this come as like that. Then this is the C2 of B, and obviously this is a C2 of Y, and this is a C1 of Z. Simply you can represent it here as a one of the edge C4 of. I think you understand that how I representing the whole every gate into the cell arc, net arc, into the timing graph. Let me complete this because it will unnecessary. I will wasting your time. So let's complete that. So now I already completed this whole combinational cutout part into the timing graph. I think if you see carefully, then you will understand. So let compute the arrival time. That how to compute the arrival time? Let's take it as source. The source vertices as a zero, zero time, and let's take it as source vertices as a zero time, and every net delay as a take 1, and if you try to give 0 1, then this point also 1, this is 1, this is 2, this point 3. So 1 and 3 I will taking the maximum one. So obviously cell delay take it as a 0. So obviously 3 here will get 4 here, then 3 cell delay, I think you have to take cell delay, take it as a 1, then you will get 4 here, 5 here, 2, then 3, 4, 0, 1, 5. So you already, I think, calculate from this point to output point that your one arrival time is taking as a 8 and 9. Just remember that you considered 0 as one of your initial timing constant, and every net delay and cell delay will 1, just a simple one. Now if I try to give a constraint for the required time, that for output one node the required time is given as a 11, and output 2 node the required time given as a 10. So it's given. If we will follow that, so 11 here and 10 here, obviously you can see there is a slack is positive here, so obviously there will be a no slack is positive here, obviously there will be a no setup violation chances. If you try to calculate, get 11 here should be 10, 9, 8, 7, 10 here it should be 9, 9, 7, so take it as a 6, minimum one take it, 5, 4, 3, 6, here it is. So now you will got 6 is your required time at the from in the backward traversal. When you go for the required time, this is your required time, and because you already constraint your, because given constraint is suggested that 11 and 10 is your required time, and 0 0 0 you start with, and net delay 1 and cell delay 1 you start with as a arrival time. So I think by this example you will understand how to just represent one data path combination, how to represent a one combinational data path into a timing graph